Hi, my name is Yingjie Xue. I'm a PhD candidate from Brown University. The paper I'm presenting is titled Hedging Against Solution Attacks in Cross-Chain Transactions. With the emergence of many different blockchains, people are interested in cross-chain transactions. For example, cross-chain swaps, where parties want to exchange their assets. Cross-chain deals, for example, auction, where an auctioneer wants to sell an item to the highest bidder. Researchers have proposed protocols for those applications. However, most of them are vulnerable to solution attacks when one party decides to halt participation in the protocol. Let's look at a two-party swap example. Suppose Alice wants to exchange her Bitcoins with Bob's Litecoins. They decide to use atomic swap to help them do that. By the atomic swap protocol, Alice and Bob first escrow their coins. After that, if all of them are compliant, their assets are swapped. If any of them deviates, they will get their original assets back. This protocol is good when both of them are compliant. However, if there is a deviating party, the protocol is problematic. For example, after Alice escrows her Bitcoins following the protocol, she is expecting Bob to do the same thing. However, Bob walks away. Then Alice is stuck since her Bitcoins are locked. This is called the lockup griefing problem, which means locking the assets temporarily is expensive. Usually, the assets are locked for at least 24 hours, which is quite a long period of time. The consequences of using the atomic swap protocol, as I show here, are if Alice's asset depreciates, Bob walks away, then Alice is stuck. Or if Bob's asset depreciates, Alice walks away, then Bob is stuck. As a result, no one wants to participate, since probably they will suffer. In real life, when two parties agree to exchange something and one party walks away, this party pays a premium to compensate the other. However, in the blockchain scenario, there's no such solution. Researchers have noticed this problem and proposed some solutions. However, their solutions are either asymmetric, that means only one party is protected from the lockup griefing problem, or their solution just works for two-party swaps. They cannot be generalized to other cross-chain transactions. In this paper, we proposed hedged cross-chain protocols to hedge against the lockup griefing problem. We have hedged protocols for two-party atomic swap, multi-party atomic swap, auctions, and brokerage. We also provide bootstrapping protocol in case two parties are exchanging a huge amount of assets. We'll get into later. We also analyze security properties by theoretical proof and model checking. Before introducing our hedged protocols, let's first look at security goals we want to achieve. Throughout this talk, I will use two-party swap as an example. As a spoiler, we will let parties first deposit some premiums before the actual atomic swap. Here, by liveness, we mean if all parties are conforming to the protocol, the swap happens and the premiums are refunded. The second security goal is safety, which means for a conforming party, it will never get a negative payoff. For example, if a conforming party deposits $1 worth premium along with $100 worth Bitcoins to swap. Then at the end, this party will get no less than $101 worth assets, no matter the other party is compliant or not. The last security goal is to hedge against the lockup griefing problem. We cannot eliminate the lockup griefing problem because whoever first escrows some assets will suffer from the lockup griefing problem if the other party just walks away. So our goal is to mitigate the risk. If in the worst case, a conforming party just locks some small premiums without compensation, we'll think it is an acceptable risk, and we will regard our protocol as a hedged protocol. We assume the premiums are 1% of the amount of assets to swap, and they are small. If they are not small, we will fix that in our bootstrapping protocol. Now, using our hedged atomic swap, if a conforming party escrows $100 worth Bitcoins to swap, which are finally refunded, this party will get no less than $1 worth asset as compensation. Let's first look at a standard atomic swap protocol, which is not a hedged one. It uses a hash time lock contract as a key component. A hash time lock contract is associated with a hash value h and a time lock t. According to the contract, before t elapses, if a designated party inputs the pre-image of h, they will get the assets in the contract. Otherwise, after t elapses, the assets are refunded to the owner. Let's look at a detailed protocol for Alice trading her Bitcoins with Bob's altcoins. First, Alice escrows her coins into a hash time lock contract with the hash value Y generated by a secret S, locking for some time. After seeing Alice's escrow, Bob escrows his coins with the same hash value Y. Since Alice knows the secret S, she can send S to redeem Bob's asset. After seeing Alice's redeem, Bob knows the secret S. He can send S to redeem Alice's asset. The lockup griefing problem arises when Bob walks away at step 2, where Alice is stuck since her coins are locked. Or if Alice walks away in step 3, then Bob is stuck since his coins are locked. To design a hedged two-party atomic swap, the trick is we let parties first deposit some premiums before the actual atomic swap protocol starts. First, Alice deposits some premiums on the Litecoin blockchain, which looks at Bob's escrow. If Bob's escrow is refunded, the premium is paid to Bob. Otherwise, the premiums are refunded to Alice. Similarly, after seeing Alice's premium, Bob deposits premium on the Bitcoin blockchain, which looks at Alice's escrow. If Alice's escrow is refunded, the premium is paid to Alice. Otherwise, it is refunded to Bob. We analyze step by step the payoff of a conforming party if the other party was away at each step. We can see that for a conforming party, it will either lock some premiums without compensation, as shown by these two blocks, or it will get some premiums to compensate locking their assets swap, as shown by these 3 blocks. Or if no party deviates, their assets are swapped and their premiums are refunded. If two parties are exchanging a huge amount of assets, locking 1% of them as premiums without compensation may not be acceptable. Here we provide a bootstrapping protocol to fix that. We start with our previous hedged two-party atomic swap, where we deposit 1% of the amount of assets as premiums. We can replace the deposition of premiums with an atomic swap of premiums and deposit premiums on premiums to protect the lockup griefing problem of the lower layer premiums. We can repeat this procedure until the premiums are acceptable small. We can see that the premiums are decreasing exponentially. Our two-party atomic swap protocol cannot be generalized to multi-party swap directly because there are some challenges. A multi-party swap can be modeled as a directed graph, where a vertex represents a party and an edge represents a proposed asset transfer. We use the graph shown on the right to show the challenge. Here, Alice knows the secret. She starts depositing premiums first. Then there's a problem. If Alice only receives the escrow from Carol, but the escrow from Bob is missing, then Alice is stuck, since if Alice releases the secret, she loses her assets. If Alice keeps the secret, she loses her premiums. To fix that, our hedged multi-party swap protocol shares the same recipe as our two-party one, that is, deposit premiums and then swap. However, we have two kinds of premiums deposited in two phases. Premium escrow, which is paid to a counterparty if the escrow does not happen. Premium redeem, which is paid to a counterparty if the redeem does not happen. The details are shown in our paper. We also provide hedged auctions and brokerage protocols, which can also be found in the paper. To be noted, different protocols require different hedging strategies. We prove the security properties of our proposed protocols by model checking. The reason why we use model checking is that our protocols can be modeled as finite state machines. Each step triggers a state transition. We use TLA plus language for our model specification. Each arc is related to a process or blockchain in our model. We simulate parties deposit premiums, escrow the assets, and redeem. Here on the right are graphs we use in our model checking. Our model checker can efficiently check the security properties for simple graphs, such as two-party swaps, three-party swaps. However, it cannot check for complicated graphs because of the state explosion. So we also provide theoretical proof for more general graphs. At a high level, our protocol can be seen as two sequential modules, a premium module and a swap module. Before the swap module starts, the conforming party only deposits some premiums. So the lockup griefing problem is restricted to those premiums. After swap module starts, the security properties are guaranteed by those contracts. Thank you. Questions are welcome.